Okay, so when you're doing dynamics problems, if you feel stuck, it can never hurt to draw a free body diagram. And so what do I mean by a free body diagram? Let's start with just some horizontal surface. And we're going to have both our X and our Y. And we are going to draw a little dot. And let's pretend that our object has all the mass in that dot. Let's hypothetically say we've got a problem where we've got some object and we're pulling it, say with a rope. Let's say we're pulling it with a rope to the right. So I'm going to draw to the right a force, and I'm going to call it FR for F rope. Okay. And let's also say that there's some friction on the surface. So let's say that the object's moving and we're pulling it with a rope to the right, but as it slides across the surface, there's some kinetic friction. Okay. So if I'm just sliding it horizontally to the right, the kinetic friction is going to be horizontal, exactly opposite. So it's going to be exactly opposite to the left. So we're going to say that this is going to be the force due to friction. And so that's our horizontal situation. We're pulling with a rope to the right, and we've got kinetic friction opposing the pulling of the rope with the rope to the right. So we also have to keep in mind that there is gravity acting straight down, and we know that the gravitational force is equal to mg. And so when you can imagine this object being pulled towards the center of the earth due to gravitational force, and then it encounters the surface, it doesn't keep it going towards the center of the earth. The ground is going to push back up. This is an action reaction pair. So imagine the action is that this object presses against the ground with mg, and the ground presses back up, and we call that the normal force. And in a situation like this, where all of our motion is contained in the horizontal direction, that means that there is no motion in the vertical direction. And if there's no motion in the vertical direction, that means that there's no velocity in the vertical direction. And if there's no change in velocity in the vertical direction, so if the velocity stays zero in the vertical direction, that means there's no acceleration either. So we've got a situation in the vertical direction. And so here's the key. We want to write Newton's second law equations for both our vertical and horizontal directions. And so for the vertical direction, I'm going to sum all my vertical forces. That sigma is a Greek symbol for sum of. And so I have upward as positive y and downward as negative y. That's typical convention. So I'm going to say that the sum of my forces in the y direction are equal to the normal force, and that's positive, it's up, minus mg, which is the gravitational force straight down, and that's going to be equal to the mass of the object. Again, the mass is all contained in that red dot, multiplied by the acceleration in the y direction. Now, going back to our rope, remember we're pulling to the right, and then we have kinetic friction opposing that motion, so it's going to the left. So what I'm going to do is I'm going to sum my forces in the x direction, and so that's going to be equal to, if we go for the convention that to the right is positive and to the left is negative, then we're going to have our force of friction positive. Just wrote that there. I want my force to the rope is positive, and I want the friction force to be negative because we're going to call left negative. So that's minus force friction. And that's going to be equal to mass times the acceleration in the horizontal. So you see those two equations, the one in orange and the one in blue? That's just Newton's second law 2 times over, one in the vertical direction and one in the horizontal direction. And so if you're stuck, it's good to account for all the forces and then write out Newton's second law equations in each dimension of interest. And then you can think about, well, how can I rewrite these equations based on what I know? And so, for example, I can unpack this blue equation some more because we know that when it comes to kinetic friction, so this term right here, we know that that is equal to the coefficient of kinetic friction, I'm going to call it mu k, multiplied by the normal force. So if you think about it, the more that the object is pushing into the ground, the more friction you're going to have, the more grinding you're going to have, if you will. That's why it's not just the coefficient of kinetic friction, but you also have to ask yourself, but how much is it actually pushing into the ground, which means that's how much the ground will push back. And so that's why you have that normal force term. And so we can unpack this more because if we look in the vertical direction, if we don't have any motion going on in the vertical direction, and it stays that we don't have any motion going on in the vertical direction, then we can say that there's no acceleration, which means that there is a sum of forces in the vertical direction that equals zero by Newton's second law. And so if that's the case, because A was zero, then I can say that the normal force is equal to mg. All right. And so this term right here goes right there. And so let's say that you were asked to solve for the force on the rope, right? You could take that blue equation and you can unpack it some more with what you know about how to account for friction. Okay. So also know that like in situations where you might have non-zero acceleration in both directions, at the end of the day, you can figure out what the composite acceleration is just by taking the components of acceleration and adding them up like vectors. So in other words, if you had a non-zero ax and you had some non-zero ay, then you could have a resultant acceleration. What I did right there is I went from the tail of the x component to the tip of the y component. But of course, you could also use the Pythagorean theorem, where if this is the net acceleration a, then you can say because of a squared plus b squared equals c squared, all right, it'd be the same thing as saying ax squared plus ay squared equals a squared. So please review the video on vector decomposition if you have any confusion about vectors still. But essentially, you're using trigonometry. And in this case, you would be using the Pythagorean theorem to take components and add them back up to get the resultant. Now, I also want to, while we're doing the free body diagrams, to show you how you can account for when you might have things at an angle. Okay, so more specifically, let's say we've got some incline. And again, let's have our object just be represented by a single dot. We're going to say the center of mass of that object. So all the mass of that object is in that red dot. Okay, and so I'm going to draw the ground here. And I'm going to say that the incline is at an angle theta from the ground. All right, so just because it's at an incline doesn't mean that the gravitational force is still pulling on this mass towards the center of the Earth. So what I'm going to do here is I'm going to draw downward mg. Okay, it's just like in the previous case, it's still straight down. Okay. However, let's say we were interested in solving a problem where we had motion along the incline. So before we even think about friction, if we just had like a mass there, imagine you just had like a ball on an incline and you let it go, you probably wouldn't be surprised if the ball would start rolling down. And why is it rolling down? Because it turns out that even though gravity is acting straight down, there's a component of gravity that is acting in the direction of the incline. You see this component right here? And remember, you can take a vector and you can decompose it into two dimensions. You can also think of the gravitational force as having a component that's perpendicular to the incline. So I want to show you a little trigonometry here for how you can decompose these vectors. So this right here is 90 degrees. All right. And so then the question becomes, okay, well, what's this angle right here? So let's call that angle phi. Remember, with a triangle, when you add up the interior angles, you're going to get 180 degrees. So if I have 180 degrees to play with, all right, and then I have my angle theta in the bottom left there, okay, then what is going to be phi? So 180 minus theta minus phi, and then minus 90. Those are our three angles, right? You have the right angle in red there. You have theta, phi. So 180 minus theta minus phi minus 90, that should give us 0, right? Those three should add up to 0, okay? Well, what is phi going to be? So I'm going to bring phi over to the right by just adding phi to both sides. So I'll have 180 minus theta minus 90 equals phi. Okay, and then you can also see I have 180 minus 90. So this is the same thing as 90 minus theta equals phi. Okay, and so again, that's this angle right here, right? So that is 90 minus theta, not theta. Okay, now remember mg is pointing straight down, so we can take that mg and we can use trigonometry. And again, refer to the video on vector decomposition to see how you can take a vector and decompose it into its components. So it can be shown with trigonometry that if mg is pointing straight down and that angle phi is 90 minus theta, then it turns out that this component that is in the direction of the incline is going to be mg cosine phi, which again is 90 minus theta. And similarly, this is going to be, and by this I mean perpendicular to the incline, mg sine phi. Okay, but again, remember, it's 90 minus theta, not theta. You have to be careful. That's why it helps to draw these out and figure out the angles. So let's say that we want to put friction in this problem too. So you've got this mg cosine phi term, which is the same thing as mg cosine of 90 minus theta. Then you have acting in the inclined direction a component of gravity that wants to make the ball roll. If it rolls, that means that there's some kinetic friction. And so we're going to have the kinetic friction opposing that rolling. So I'm going to call that the force of friction. And so similarly, we have to figure out we have a coefficient of kinetic friction multiplied by a normal force. Well, what is the normal force? The normal force is going to be how much the incline pushes back up on the ball. And so I'm going to represent it like this. We're going to call that the normal force. And do you see how it opposes the mg sine phi term? Which again is the same thing as mg sine cosine minus theta. So in this case, the pressing on the surface, if you will, isn't as much as it was when it was horizontal, because now only a part of gravity is oriented perpendicular to the surface. When all of gravity is perpendicular to the surface, that ball is being pulled down on the surface at its maximum amount, and therefore the surface is pushing back. Now only some of gravity is pulling the ball against the surface, if you will, meaning that the surface is pushing back not as much as it was if this situation was completely horizontal. Okay. So, like before, we could say if there's no motion that is perpendicular to the surface, then we can say the normal force minus mg sine phi, that's going to be equal to 0. Okay. And meanwhile, we can say with respect to the motion along the inclined plane, depending on what direction you want to have as positive and negative, let's just, for the sake of it, say that as it rolls down, that'd be its natural inclination. We'll call that positive. So we would have mg cosine phi minus, and then remember the friction, mu k Fn. And so here's the thing, we can unpack this some more. We're going to say that that's going to be equal to the mass times the acceleration along the incline. And remember, we have the normal force, that is the incline pushing back up on the ball, that is equal to mg sine phi, which is the same thing as mg sine 90 minus theta. So you see how we unpack that there? So this is why it's important not just to think, oh, well, horizontal is always going to be cosine term and vertical is always going to be sine term, because it depends what your angles of interest are. And it also depends how you define your X and Y. In this case, the motion wasn't all in X or all in Y, but it was at an incline. So hopefully you've enjoyed these tales from the whiteboard.